fellow mathematicians. We're going to take a look at the method of undetermined coefficients, which is the first method that you learn about to solve non-homogeneous differential equations. So let's get started with the terms. What we call a non-homogeneous ODE is one in which the right-hand side is not 0. So maybe the right-hand side is a function of x, maybe it's just a number like 1, but as long as the right-hand side is not 0, we call that a non-homogeneous ODE. Now, if the right-hand side is 0, that gives us what we call the homogeneous ODE, and we can actually solve that already very quickly by converting to the characteristic equation. You might recall from a previous video, the characteristic equation has 3 possibilities for solutions. The characteristic roots come out to either be distinct real roots, a repeated real root, or you get complex roots. The only change is these solutions, we now call them the complementary solution. More specifically, the complementary solution, that's the solution to the homogeneous ODE, where the right-hand side is 0. Now, when I introduce the method of undetermined coefficients in class, I always tell my students that your first step should be to find the complementary solution. And that's because we're going to see in some tricky or exceptional cases, we actually have to use that to make a choice to implement the method of undetermined coefficients. We'll get to that a little bit later. All right, so first, step 1, we always look for the complementary solution. Step 2, what we use undetermined coefficients for is to find what we're now going to call the particular solution. And what the particular solution does is it's a function such that when we plug it in to the differential equation, we're left over with not 0, but a function of x. In class, I always like to rewrite this. I can put a 0 here. That doesn't change the differential equation, but this is a reminder that you look for 2 different parts as your solution to the non-homogeneous ODE. The first part you look for is the solution that gives you 0. That's the complementary solution. And then you use undetermined coefficients to find the particular solution, which is what gives you g of x left over. The full solution to the non-homogeneous ODE is what we would write as a combination of the complementary solution plus the particular solution. And this probably looks familiar from in class. Your full solution is what we call yc plus yp, the complementary solution plus the particular solution. Again, the method of undetermined coefficients, that tells you what the particular solution is. Now, undetermined coefficients is usually a very simple method to apply, and its simplest form, what we do is we choose a form for yp based off of g of x. And again, g of x, that is the non-zero right-hand side of the non-homogeneous ODE. Now, before we get to some examples, we need to address 1, why this works, and 2, when the method of undetermined coefficients applies. So let's go ahead and get to that, why this method works, and when it applies. So, to apply the method of undetermined coefficients, we go to our non-homogeneous ODE, we take a look at our right-hand side, g of x, and we use that to make a choice for the form of what we call the particular solution. Now first, why does this work? To answer that, we're going to go back to Calc 1, when you first learned some basic derivative rules. So we have 3 examples here. As a differential equation students, these are going to be really easy, but we're going to kind of step back and see if we can generalize these from specific examples to more general properties. All right, the first example, very simple, just a combination of powers of x. We just use the power rule. Next example, we can differentiate it using the chain rule. And then the last example, your basic trig derivatives, which shouldn't be a problem for you as a differential equation student. Now, to address why the method of undetermined coefficients works, in other words, why choosing yp based off of g of x, why that works, let's generalize this. Here we have a polynomial, and the derivative is also a polynomial. Here we have an exponential function. The derivative is another exponential function. In the third example, we have a combination of sine and cosine, and the derivative is a combination of sine and cosine. Now, if we, again, step back, we might be able to see that we can write generalized versions of these. The first one, we might write it as the derivative of a polynomial is another polynomial. Second example, the derivative of an exponential function is another exponential function. So we might write that the same way. The derivative of an exponential is another exponential. And the last example, a combination of sine and cosine differentiates to a combination of sine and cosine. And we're going to write that as the derivative of a sine or cosine or combination thereof differentiates to the same thing. And notice here, the generalized properties, they all have the same form where we differentiate a type of function and we get the same type of function back for the derivative. And that's why the method of undetermined coefficients works if g of x is a combination of polynomials, exponentials, and sines and cosines. Then when we differentiate that choice for yp, we get those same types of functions back. So there's a very short answer to why the method of undetermined coefficients works. Now, more importantly, what this addresses is when undetermined coefficients applies, and it applies when g of x is a combination of these 3 types of functions. So when g of x is a combination of polynomials, exponentials, and sines and cosines. And you can see there's some limitations to this. If g of x were, for instance, tangent of x, undetermined coefficients would not apply. Let's point out why. Let me write down the basic derivative rule. The derivative of tangent, you know that as secant squared. And this breaks the pattern here. Notice sine and cosine differentiate to themselves, but tangent does not differentiate to a tangent function. Tangent differentiates to a secant squared, which is a more complicated squared trig function. So be careful here. We're not saying the derivative of a trig function is a trig function. That is true, but only sine and cosine differentiate back to the same type, back to a sine or cosine. That is the second part we need to address. When the method of undetermined coefficients applies, if g of x is a polynomial, exponential, combination of sine and cosine, or a combination of any of those, then you can apply the method of undetermined coefficients. If g of x is not one of those functions, like for instance, if g of x is tangent of x, we need another method to find the particular solution. We'll get to that in another video, but for now, let's get to some examples. There is a little bit of skill to choosing the right form for yp, and let's go through a lot of examples to make sure that you can choose the right form for yp right from the beginning. So let's take a look at a specific non-homogeneous ODE, y double prime minus 6y prime plus 8y equals g of x, and we're going to change g of x and see how that influences our choice for the form of the particular solution. Now, as we mentioned in a previous part, step 1, go ahead and always first find your complementary solution, solve the homogeneous ODE, and you should find you get characteristic roots positive 2 and positive 4, and you get as your complementary solution a combination of e to the 2x and e to the 4x. That's going to play a role in the tricky or exceptional case to undetermined coefficients, which we'll be getting to in the next part. All right, so let's go to our first non-homogeneous ODE, where g of x, the right-hand side, is perhaps 3x plus 1. Now, what we want to look at this right-hand side as is we want to identify it as what type of function it is. It's a polynomial, and it's a polynomial of degree 1. So what we try for the form of yp is a general degree 1 polynomial, which looks like ax plus b. A and b are our undetermined coefficients, constants that we determine by plugging this form for yp back into the non-homogeneous ODE. All right, let's go to the next one. This g of x is a degree 2 polynomial, so we might try a general degree 2 polynomial, ax squared plus bx plus c. All right, let's go to the next example. If g of x is e to the 3x, now that's an exponential function, and just think how you would differentiate that with the chain rule. The chain rule is going to give you factors of 3 in front, but the chain rule will never change the exponent. You'll always have e to the 3x. The general version here is we just have a constant in front, a times e to the 3x. And again, due to the chain rule, the exponential function should be the same type of exponential function here. All right, now we move on to combinations with sine and cosine. So perhaps here g of x is sine of x. Think of how sine and cosine differentiate in combinations with a first and second derivative. If you differentiate sine, you get cosine. Differentiate that again, you get negative sine. So when we have a sine term in g of x, we might need to include a cosine term in the particular solution. Remember, sine and cosine differentiate back to a combination of sine and cosine. So what we try for yp in this case is a combination a sine of x plus b times cosine of x. All right, now we start getting into the examples that are combinations of polynomials, exponentials, sines and cosines. Here, x, we're going to think of that as a degree 1 polynomial, and it's multiplying an exponential function. So we generalize that. We take the form for a degree 1 polynomial, and we multiply it by that exponential. So we might try ax plus b times the exponential e to the negative x. Now, in class, students usually ask me, is it wrong if I include a constant in front? Let me go ahead and write that down. So maybe you would try this as ax plus b times c e to the negative x. And this is not wrong, but it's introducing unnecessary constants, because notice I can multiply this constant c into the parentheses, and c times a is another constant. So you don't need to include this c here, since this form already fully generalizes it. All right, let's move to the next example where the right-hand side is x times cosine of 2x. We're going to combine this degree 1 part, kind of like we did here, but also with how we chose the particular solution when we have a sine or cosine term. Now, the chain rule, when you differentiate cosine of 2x, the inside will always remain 2x. So we might try here for yp a degree 1 polynomial, ax plus b times cosine of 2x. And whenever we have a sine or cosine, we always need to include the other one. So we have another degree 1 polynomial. So I guess cx plus d times sine of 2x. All right, you're probably starting to get a sense for this and see the patterns here. Here we have a degree 2 polynomial times a sine function. So we generalize that and have a general degree 2 polynomial times sine, and then a similar version times cosine. We get a lot of constants here, a lot of undetermined coefficients. Writing down the first term, a degree 2 polynomial would look like ax squared plus bx plus c times sine of x. But whenever you have just a sine or cosine, you always include the other, but now it's multiplied by another degree 2 polynomial. So 3 more constants. Dx squared plus ex plus f times cosine of x. All right, now those are your simple combinations of polynomials, exponentials, sines and cosines. But what if we start adding combinations of those together? Like this last example, notice we have a degree 2 polynomial plus an exponential. Well, we can basically add our regular choices for the form of the particular solution of each part. So here we might try a general degree 2 polynomial and then plus a general exponential function. So that might look like ax squared plus bx plus c. That takes care of the form of the particular solution for 4x squared. But we might also include another term in the particular solution, a generalized exponential function. We might go with d times e to the 3x. And these are generally all your simple combinations, almost all the examples that you will see in your differential equations course are probably combinations very much like that. And that's generally what I give for examples in class and on my exams in differential equations. Now, earlier we did mention the complementary solution plays a role sometimes in choosing the form for the particular solution. So before we end this video, let's go ahead and get to that. In our final part here, we're going to take a look at where your initial choice for the particular solution might break down. And this is a little bit tricky, but you can get the hang of it. So let's suppose our non-zero right-hand side were maybe e to the 2x. Now be careful, we saw an example earlier where the right-hand side was e to the 3x. Very straightforward, right? Well, let's suppose we tried that here. We have an exponential function. We might try a general exponential function of the form a times e to the 2x. Now you can go ahead and try that, but you'll find something funny happens when you plug that into your non-homogeneous ODE. What happens with e to the 2x for this differential equation? Well, e to the 2x, when you plug it into your differential equation, that's going to be part of the solution that gives you 0. E to the 2x is part of your complementary solution. And this term, the right-hand side, is duplicated within the complementary solution. So no matter what you choose in front, maybe a constant, when you plug this in to your differential equation, that right-hand side is going to give you 0. It's not going to come back to e to the 2x. Now, how we modify this is by including a factor of x in front. So instead of our initial choice, that's duplicating e to the 2x, rather what we try is our basic choice for the particular solution, but multiplied by a factor of x. So the fix here is we include a factor of x for each duplication of the form of our particular solution in the complementary solution. All right, and with practice, you can get the hang of this. Some trial and error is usually involved, but you should very quickly find if your initial choice, like a e to the 2x, works. In this case, it wouldn't for that differential equation, but multiplying by a factor of x to your initial choice for yp. So instead of a e to the 2x, we try ax times e to the 2x. That would work for your particular solution here to this non-homogeneous ODE. All right. I hope you enjoyed the content, all the different parts and examples that we covered. If you did, support the channel. Make sure to like and subscribe.